Good morning, everyone. Thank you for attending my presentation. I'm Zhou Yu from Tsinghua University, and I'm here to present our work, Truman, Constructing Device Behavior Models from OS Drivers to Fuzz Virtual Devices. This is a collaborative work involving Tsinghua University, Zhongguancun Lab, and the EPFL. Today, I will discuss the importance of hypervisor security, the challenges in fuzzing virtual devices, and how our tool, Truman, handle these challenges effectively. Cloud computing has transformed the way resources and applications are managed. The heart of the cloud computing are hypervisors, which manage virtual machines and ensure efficient sharing of hardware resources. Major cloud providers like AWS and Azure rely on hypervisors for isolation, scalability, and security. However, their critical role also makes hypervisor a prime target for attackers. The hypervisor serves as a critical layer in the virtualization environment, acting as a bridge between the host hardware and virtual machines. As shown in the figure, the hypervisor manages communication with virtual devices, which interact with the guest operating system through device drivers. Virtual devices use mechanisms such as PIO, MMO, or DMA to facilitate communication and emulate hardware. However, this complexity also introduces vulnerabilities. Bugs in the virtual devices can be exploited by attackers to escape the virtual machine. Building on the structure introduced earlier, these slides illustrate how vulnerabilities in virtual devices can be exploited by attackers. A malicious guest OS can target virtual devices using flaws in mechanisms such as PIO, MMO, or DMA. For example, an attacker might craft malicious inputs that exploit how a virtual device processes messages. This could lead to memory corruption, allowing the attacker to execute arbitrary code. Past research on virtual device fuzzing has explored several areas. Tools such as Hypercube and Nix focus on the environment, providing tailored platforms of fuzzing, but often lacking deeper semantic analysis. Other tools such as VDF targeting the interface, particularly the PIO and MMO interfaces. Grammarly-based fuzzers like vShuttle and Morphuzz improve input generation by defining device-specific grammars, but this process is manual and time-consuming. Semantic focused tools, including VDAZZLE, infer device behavior from the source code of virtual devices, but they struggle with generalization across different virtual devices. These gaps highlight the need for a tool like Truman, which combines automation, dependency extraction, and systematical fuzzing to address these challenges. One of the key challenges in fuzz virtual devices is managing the dependencies in device communication. Virtual devices follow a strict sequence of operations, such as setup, configuration, operation, and cleanup. And any violation from this order can result in invalid inputs that fail to test the device properly. In addition to the sequence, individual messages also have field-level dependencies. For instance, a register might have multiple components that depend on each other, or a nested DMA buffer structure may require a specific pointer relationship. These intra-message and intra-message dependencies are crucial for accurately testing device behaviors. Truman automates the extraction of both inter- and intra-message dependencies, ensuring more effective and comprehensive fuzzing. The second challenge in fuzzing virtual devices involves understanding state dependency. In this context, state dependency refers to the set of inter- and intra-message dependencies that are valid in a specific state of the device. This challenge becomes even more difficult for but-hidden devices, such as those using the virtio protocol, where devices are not directly accessible. Without visibility into these states, it's hard to craft efficient fuzzing inputs. Truman tackled this challenge by systematically analyzing device drivers and the bus drivers to infer state dependencies. Our key insight is that while virtual devices are often closed source, their corresponding drivers are typically open source. This is because device driver, which operate within the guest operating system, must be accessible to developers and adhere to standard specifications. And these specifications defines how the virtual device and its driver should interact, including message formats, field relationships, and expected behaviors. The virtual device and its driver essentially act as two sides of the same coin, following the same specifications. For example, the device driver implements the logic to handle device communication, while the virtual device emulates the hardware to respond to these interactions. By analyzing the open source driver, we can reconstruct the behavior models of virtual devices with a high accuracy. Truman leverages this relationship to extract intra-message, and state dependency from open source drivers. These behavior models form the foundation for efficient dependency-aware fuzzing that systematically explores the functionality of virtual devices. Truman's design is built around the two-step framework to address the challenges of fuzzing virtual devices comprehensively. The first step is to extract inter- and intra-message dependencies. By analyzing open source drivers, Truman reconstructs the logic relationships between device messages and their internal feeds. This ensures that all fuzzing inputs adhere to the required dependencies, avoiding invalid sequences that fail to test meaningful behaviors. The second step is to implement a dependency-aware fuzzing engine. This engine mutates messages and sequences systematically at various levels. This structured approach allows Truman to explore device behavior deeply and discover vulnerabilities that traditional tools might miss. By combining these two steps, Truman bridges the gaps in existing fuzzing techniques, offering a more robust solution for virtual device fuzzing. To effectively test virtual devices, it is essential to cap both inter- and intra-message dependencies. For inter-message dependencies, Truman uses a call graph and control flow graph traversal. By analyzing how these messages interact, Truman ensures that fuzzing respects the required order of operations. For inter-message dependency, Truman exploits backward data flow analysis. This method traces how individual fields within a message depend on each other. Another critical component of Truman's design is its ability to analyze state dependencies. For example, certain operations may only be valid during the initialization state, while others are specific to an operational or error state. To analyze these dependencies, Truman examines interactions between the bus driver and the device driver. This allows it to infer the device internal states and how they influence message handling. By understanding these states, Truman generates fuzzing inputs that are tailored to specific contexts, ensure meaningful exploration of device behaviors. This state-aware approach is particularly crucial for bus-hidden devices, such as those using the virtio protocol, where internal states are not directly observable. Traditional tools struggle to handle these scenarios, but Truman systematically discovers vulnerabilities by accounting for state dependencies. Truman's dependency-aware fuzzing engine is designed to perform generation and mutation at multiple levels, enabling comprehensive testing of virtual devices. At the message level, Truman can modify individual fields within a message to explore how changes affect the device behavior. At the sequence level, Truman tests how alerting the order of our combination of messages impact the device. This helps discover vulnerabilities in how the device handles transitions between states, such as immune from configuration to operational state. At the state level, Truman explores how the device behaves under specific internal states. By simulating different contexts, it ensures that the fuzzing process reaches deep, hidden code paths that are often missed by traditional tools. Truman was evaluated against leading tools such as Morphuzz, VDazzle, and AFL++. It achieved higher code coverage in 19 out of 29 devices. Higher code coverage reflects better exploration of target system, which increased the likelihood of discovering vulnerabilities. These results demonstrate Truman's ability to comprehensively test virtual devices. Truman's evaluation demonstrates its effectiveness in discovering both known and new bugs across major hypervisors, including QEMU, VirtualBox, VMware, and Parallels. In terms of known bug discovery, Truman successfully identified vulnerabilities that have been previously reported. This validates its ability to thoroughly explore device state and generate inputs that replicate complex bug conditions, providing confidence in its accuracy and coverage. Beyond known coverage, Truman discovered 54 new vulnerabilities, including 6 CVEs. In summary, Truman introduced a novel approach to fuzzing virtual devices by automating dependency extraction and enabling dependency-aware fuzzing. Our results demonstrate its effectiveness with high code coverage and significant vulnerability discovered. We believe Truman represents a step forward in securing hypervisors, and we invite collaboration through our publicly available source code on GitHub. And that's all. Thank you.
Okay. Thanks again for your presentation. Very clear, very interesting. So I invite the audience who wants to raise a question. All right. So I go with that. Can you elaborate a little bit about the static analysis used to analyze the code and what could be the limitation of the static analysis?
For the static analysis, we should first compare the device driver to the ARM interpreting representation, the ARM IR, and then we use the methods such as SVF to help us analyze the device driver, and we conduct the flow-sensitive, path-sensitive, and field-sensitive static analysis to extract the we mentioned the inter-message dependency and intra-message dependency and state dependency graphs to build our device behavior model.
All right. And last question is, do you think your approach can be applied to other scenarios where you have this combination of open source implementation and closed source programs?
Yes. The Truman applies both the open source hypervisors such as QEMU, VirtualBox, and the closed source hypervisors such as VMware Parallels. We also find some bugs and crashes on both the open source hypervisors and closed source hypervisors.
Okay. Thanks. Let's do another round of applause for our speaker.